This is a review of kinematics for the AP Physics B class. We basically break down kinematics into two main topics, one-dimensional motion and two-dimensional motion. And let's look first at one-dimensional motion. There's constant velocity and constant acceleration. Now, we need to remember what the difference is between constant velocity and between speed and velocity. Remember, speed is a scalar, and it only involves magnitude, whereas velocity is the vector, and it involves both magnitude and direction. The constant velocity equation comes from one of our kinematics equations, where the initial position we assume to be 0 and the acceleration becomes 0. So essentially this is our equation. Remember, many times we write it like this, where v is equal to x over t. So average velocity essentially is written this way, where the velocity is equal to the change in displacement. So that's displacement divided by the change in time. Now we've got to be able to solve problems using average velocity. So in that case, we would use motion maps and the strategy, the kinematic strategy. Another thing that we need to be able to do with constant velocity is to graph. So if we look at a position time graph and we had constant velocity, this is what it would look like. We would have to use our strategy, our mnemonic that tells us that anytime we go in this direction, we need the slope. So since we're going from position to velocity, down here I'm going to draw the velocity time graph. This is a medium positive slope here on my position time graph. So a medium positive velocity would look like that. And now I got to go from velocity to acceleration. So in my acceleration time graph, I would go back and look at my velocity time graph, and that velocity time graph has got a 0 slope. So I replace the word slope with acceleration, and that would mean I have a 0 acceleration. All right? Then there's also constant acceleration problems. These are the three equations. You need to memorize those three equations, those three kinematics equations. You need to be able to solve problems where the acceleration is not equal to gravity, and problems where the acceleration is equal to gravity. So essentially, these would be the gravity problems, and the other would be the non-gravity problems. Free fall is what they're called sometimes. And again, we would use the motion maps and the strategy to solve those types of problems. There are also graphing problems that must be done with constant acceleration. Instantaneous velocity is definitely a topic we need to know. So if we got a position time graph, if we were to draw the instantaneous velocity at a particular point, maybe we would draw a tangent line to that point and find the slope of that tangent line. There's also the topic of instantaneous acceleration. So instantaneous acceleration would be on a velocity time graph, where let's say we're doing that. We would do the same thing. The slope of the tangent line would tell us the instantaneous acceleration. So instantaneous velocity comes from the slope of the tangent line of position time graph. Instantaneous acceleration would come from the slope of the tangent line of the velocity time graph. Okay, so there's also graphing that we would have to do. So for constant acceleration, if I had one of the possibilities would be a graph that would look like this. So the velocity time graph, I would need to go from there to there, and I would use the slope. So the slope would at first here would be 0, So that means I have a zero velocity. Then here I would describe that slope as being positive and constant. And then here I would call this slope a high positive constant high positive constant slope right there, as opposed to that medium positive constant slope. Oh, I'm sorry, medium positive slope. So later on, I would have a high positive velocity. So that's what that would look like. And then from going, so we went from x to v, now we need to go from v to a. So we look at the velocity time graph and we say that that is a medium positive constant slope. So the acceleration would be a medium positive constant acceleration. So this is what a medium positive constant acceleration would look like. Okay, next is two-dimensional motion. Two-dimensional motion, the really important topic there is that there's an independence of the horizontal and vertical vectors. That means the horizontal vectors do not affect the vertical vectors, and the vertical vectors do not affect the horizontal vectors. So there's also some graphing that's involved with that. So if we look, let's use an example of an object that is shot from ground level and follows kind of that trajectory there. Let's look at the horizontal and vertical motion. So let's call this the position, the horizontal position versus time, the horizontal velocity versus time, and the horizontal acceleration versus time. In the x direction, if we just take the x direction, the motion would look like this, where the velocity is positive and constant. So that would be a positive constant velocity because the position time graph is a positive constant slope. I replace the word slope with a positive with the word velocity, so that becomes a positive constant velocity. Then to go from velocity to acceleration, because we're going in this direction, again we're taking the slopes, I would describe the velocity time graph as being a zero slope, so my acceleration would be a zero acceleration. Now, the motion in the y direction for an object would look something like this for that particular object, the position time graph. So it's vertical velocity versus time would look something like this. Then we would take the slope of that to find the acceleration time, and that would be a negative constant acceleration. And if we assume that this is on Earth, this value there would be negative 9.8 meters per second squared. All right, so in solving these types of problems, we would use these equations. Generally speaking, in the vertical, because we would assume that there's vertical acceleration, we would use those three equations. In the horizontal, we would use this equation here, which remember is just written x over t. So we would solve problems using those vertical equations and that horizontal equation. We would use motion maps and the strategy in 2 dimensions for objects launched horizontally. Now, if we look very carefully, notice that the horizontal components always remain constant, so there's no acceleration in the horizontal. In the vertical, the acceleration is downward because the velocity arrows increase on the way down. There's also objects launched at an angle, and again, if you look at the horizontal velocities, the red arrows there, they remain constant, so the acceleration is still 0 in the horizontal. In the vertical, the velocities are increasing on the way up, coming to a stop, then increasing on the way down, with the acceleration arrows always pointing downward. Okay, and then there's also objects launched at an angle from a height. So that, for example, would be if, let's say, maybe you're hitting a golf ball from a certain height up to another height. Objects, so that's what we call an object launched at an angle from a height. Actually, it would be the opposite. It would be if you were going this way. Okay, and then the object would eventually go in this direction. So I had that opposite of the way it should be. What I actually drew was objects launched at an angle to a target. And that would look like this. So if I had a target up here and I was launching something, that's what that would look like.